which they call a distance 7 surface code, had half the error rate of a logical qubit encoded across a 5x5 grid, which is a distance 5 surface code. And that distance 5 logical qubit had half the error rate of a distance 3 logical qubit. Every time the grid size increased from one level to the next, the logical error rate was cut in half, exponentially. This is what below-threshold behavior looks like in practice, and it is the long calculations without errors accumulating and destroying the result is now a matter of engineering rather than physics. The physics works. The threshold has been crossed. What remains is building systems large enough to encode enough logical qubits to tackle the problems that matter most. Google's own leader of quantum AI, Hartmut Neven, described this achievement in stark terms. He said that with Willow, the company has cracked one of the central challenges that has been standing in the way of quantum computing for almost 30 years. That is not marketing language. That is a physicist describing a result that changes the technical trajectory of an entire field. Hit the like button right now, because the implications of this extend far beyond the quantum computing research community. Let's talk about the performance benchmark alongside the error correction result, because the two together paint a complete picture of what Willow actually demonstrated. The specific benchmark task is called random circuit sampling, abbreviated RCS. It involves applying a random sequence of quantum gate operations to a set of qubits, and then measuring the output distribution. The task has no direct practical application, but it has a specific mathematical property that makes it a clean test of quantum advantage. The computational cost of simulating a random circuit sampling experiment on a classical computer scales exponentially with the number of qubits and the depth of the circuit, meaning the number of sequential gate operations applied. As you increase the number of qubits or the circuit depth, the classical simulation burden explodes so fast that even the most powerful supercomputers hit a wall. Google ran Willow through an RCS benchmark using all 105 qubits at a circuit depth large enough to push the classical simulation cost to what they calculated was 10 septillion years on Frontier, which, at the time of the announcement, was the fastest supercomputer on Earth, built and operated by the Oak Ridge National Laboratory. Willow completed the same calculation in approximately 5 minutes. The team then explicitly addressed the IBM criticism that had followed the Sycamore result 5 years earlier. They showed that the gap between Willow and classical computers on RCS at this qubit count and circuit depth isn't just large. It's at a scale where no improvement to classical algorithms can meaningfully close it, because the exponential relationship between circuit size and classical simulation cost means that as Willow gets bigger, the classical simulation cost doesn't just stay ahead. It runs away from classical machines at what Google's own researchers described as a double exponential rate. From 10,000 years with Sycamore in 2019 to 10 septillion years with Willow in 2024, with the gap growing by a factor of roughly 1 trillion in 5 years and accelerating. That trajectory, not any single benchmark number, is the answer to anyone who argues that classical computers can catch up. Don't forget to subscribe, because Google's roadmap for where Willow goes from here is exactly what the next part of this video covers. In November of 2025, Google published what it calls its 5-stage roadmap to quantum utility, providing the clearest public statement the company has ever made about its timeline and targets for turning quantum hardware into something that does real work in the real world. The 5 stages move from exploratory quantum algorithms, which is roughly where the field sat before, genuinely beyond the reach of classical computing. Google has positioned Willow as having crossed into the 3rd stage, fault-tolerant operation below the error correctio and threshold, and has set a target of demonstrating verifiable real-world applications within the next several years. He company has specifically named quantum-enhanced sensing, materials science simulation, pharmaceutical molecule simulation, and optimization problems as the application areas where they expect to demonstrate quantum advantage on practically relevant tasks during the 2026 to 2029 window. Each of these represents a category of problem where quantum mechanics offers a structural advantage that cannot be engineered away by building a faster classical computer, because the problem being solved is inherently quantum mechanical in nature. Simulating how a drug molecule interacts with a protein target is an exponentially hard problem for classical computers, because the underlying physics of molecular electron behavior is governed by quantum mechanics. A quantum processor that can represent and manipulate quantum states directly can approach these simulations in a way that sidesteps the exponential classical scaling problem at its root, not by being faster, but by being the right kind of machine for the problem. The Quantum Echoes experiment that Google published in October of 2025 reinforced that the roadmap isn't theoretical. The Quantum Echoes algorithm is a technique designed to probe the information scrambling behavior of quantum systems in a regime that classical computers cannot simulate. Google's team applied it to Willow and demonstrated what they called verifiable quantum advantage in physics simulation, meaning a result that can be independently verified as correct using physical theory, but cannot be reproduced by any classical simulation at comparable problem sizes. This is a qualitatively different kind of result from the RCS benchmark, because it involves a calculation with direct scientific relevance. Physicists actually want to understand quantum information scrambling. It's connected to questions about black hole physics, quantum thermodynamics, and the behavior of complex quantum many-body systems that appear in condensed matter physics. The ability to use a quantum processor to experimentally probe these questions in regimes that classical simulation cannot reach means that Willow is already being used as a scientific instrument, not just a benchmark machine. And that shift from benchmark device to scientific instrument is exactly what the transition from quantum advantage to quantum utility looks like in practice. Like and subscribe now, because the parallel universes angle that came out of this experiment is something almost no mainstream outlet covered properly. Genuinely uncomfortable. Where exactly were all those calculations happening? A classical computer processes information in one physical world using one sequence of operations with a definite outcome at each step. Willow's calculation, producing a result in 5 minutes that classical simulation would require 10 septillion years to reproduce, seems to involve an amount of concurrent information processing that no single physical system operating in one universe following one causal chain should be able to accomplish in that time. Hartmut Neven, the founder of Google Quantum AI, directly addressed this in his public statements following the Willow announcement. He said the results lend credence to the many worlds interpretation of quantum mechanics, the idea originally proposed by physicist Hughes Everett in 1957 and developed extensively by David Deutsch, that quantum computation occurs across multiple branch S of a universal wave function simultaneously. In plain language, the calculation may have happened in parallel across many parallel universes, with the branches interfering constructively to produce the correct answer in the branch we observe. This is not a fringe interpretation among physicists. It is one of the most seriously discussed interpretations of quantum mechanics, and Neven was making a specific claim grounded in experimental data when he invoked it. Whether or not you find the many worlds interpretation compelling, the fact that the founder of Google's quantum program is publicly connecting his experimental results to it tells you something important about how seriously the people closest to this technology take the philosophical implications of what Willow has actually demonstrated. Let's also address the skeptics directly, because intellectual honesty requires it, and because the strongest version of the skeptic's argument helps clarify exactly what Google has and hasn't proven. The strongest skeptical position on Willow is not that the results are wrong. The results are published in Nature, independently reviewed, and the performance numbers are not seriously disputed. The strongest skeptical position is about interpretation. The RCS benchmark, critics note, is a synthetic task specifically designed to be hard for classical computers and easy for quantum computers. It doesn't prove that quantum computers can outperform classical machines on any problem that anyone actually wants to solve. The error correction result is impressive, but going from below threshold behavior with a handful of logical qubits to the thousands of high-quality logical qubits needed for commercially relevant quantum algorithms is an enormous engineering challenge that could take many years to overcome. Google itself now prefers the language verifiable quantum. Advantage rather than quantum supremacy, a deliberate choice that acknowledges these milestones are incremental rather than absolute. All of that is fair, but here is what the skeptical framing gets wrong. Crossing the error correction threshold isn't like winning a sprint and then being done. It's like proving that the road to the destination actually exists. Before Willow, there was a genuine open question in quantum computing, whether error-corrected quantum systems would get exponentially better as they scaled, or whether some unforeseen physical obstacle would prevent the theory from being realized in practice. Willow answered that question. The physics works, the threshold is real, and the double exponential rate at which the quantum classical performance gap grows as quantum systems get larger means that the engineering challenge of building bigger systems is not a race against an opponent who can keep pace. It's a race that classical computing cannot mathematically run. The broader competitive landscape that Willow sits inside is also worth understanding, because Google is not the only serious player racing toward practical quantum computing. IBM's quantum roadmap targets fault-tolerant quantum computing by approximately 2030, with a modular architecture that links multiple quantum processors together using quantum communication to build systems larger than any single chip can support. Microsoft's Majorana 1 chip, announced in February of 2025, uses topological qubits, a physically different approach that is theoretically far more stable than superconducting qubits, but remains at an early stage of development, with independent scientists publicly questioning specific claims Microsoft has made about the underlying physics. Atom computing, using neutral atom qubits with coherence, times measured in seconds rather than microseconds, has already crossed the 1200 physical qubit threshold and delivered a commercial on-premises system to a paying customer. IonQ, using trapped ion qubits, is scaling toward hundreds of high-quality qubits with gate fidelities that compete favorably with superconducting systems. What is striking about looking across all of these programs simultaneously is that they are converging on similar conclusions from different physical starting points. The threshold is real. Error-corrected quantum computing is achievable. The race is now about who can scale the fastest while maintaining the quality needed for the error correction to keep working as system size grows. Google's Willow result means that race now has a definitive frontrunner heading into 2026, with an error correction result that is the most complete and most thoroughly documented demonstration of below-threshold operation that anyone in the field has published. What this all ultimately means is worth stating plainly, without hype, and without the kind of reflexive skepticism that has sometimes caused observers to undersell what quantum computing has actually achieved. Google's Willow chip demonstrated two things that are genuinely unprecedented. It showed that quantum error correction works below the threshold in exactly the exponential way the theory predicted, transforming fault-tolerant quantum computing from a theoretical possibility into a demonstrated engineering path. And it showed a performance gap against classical computing that grows at a rate no improvement in classical hardware or software can keep up with, because the gap's growth rate is governed by fundamental mathematics rather than by the quality of classical chips or algorithms. These two factors together mean that the question is no longer whether quantum computers will eventually surpass classical computers on an expanding class of important problems. They will. The question is how long the engineering work of scaling from today's systems to tomorrow's fault-tolerant machines will take, and which companies, which national programs, and which research teams will be the first to get there. Google has planted the clearest marker yet on the path. The race to reach the finish line is the most consequential technology competition of the next decade. And Willow is the moment when the entire field looked up, looked at each other, and understood for the first time that the finish line is real. Let us know in the comments which application of quantum computing you think will arrive first and matter most, and we will see you in the next video. Google just built a computer chip that may have done something no human technology has ever done before. It finished a calculation in under 5 minutes, a calculation that would take the fastest supercomputer on Earth 10 septillion years to complete. Before we go further, smash that like button because the explanation Google itself gave for this result is stranger than almost anything in science fiction. This chip is called Willow, and Google unveiled it in December of 2024. It's a quantum chip, which means it doesn't compute the way your laptop or phone does. Normal computers process information as bits, simple ones and zeros, one after another. Quantum chips use something called qubits, tiny particles that can exist as a 1, a 0, or some strange mixture of both at the same time. This is not a metaphor. It is one of the strangest, most well-tested facts in all of physics. Think about the famous thought experiment of Schrödinger's cat. A cat is sealed in a box with a mechanism tied to a random quantum event. Until you open the box and look, the cat is treated, mathematically, as both alive and dead at the same time, a blur of both. Subscribe right now because what Google's own scientists said about this chip is going to blow your mind. Willow was put through a brutal test called random circuit sampling. It's a benchmark specifically designed to push quantum hardware to its absolute limit. Google reported that Willow completed this benchmark in under 5 minutes. To put the device in perspective, one of today's fastest supercomputers would need 10 septillion years to do the same task. 10 septillion is a 10 followed by 24 zeros. That number is so large it doesn't just exceed a human lifetime. It exceeds the entire age of the universe itself, many times over. Like and subscribe if that number just made your brain hurt. Because Google's explanation for how this is even possible is where things get truly wild. Hartmut Neven, the founder of Google Quantum AI, wrote something in the official announcement that most people glossed right over. He said, "This result lends credence to the idea that quantum computation occurs in many parallel universes, in line with the idea that we live in a multiverse." Read that again. A senior executive at one of the largest technology companies on Earth, in an official public statement, suggested that Google's chip might be tapping into parallel versions of reality to perform its calculations. This wasn't a slip of the tongue or a casual joke. Neven was referencing a real, decades-old scientific idea called the many worlds interpretation, first proposed by physicist David Deutsch. Deutsch laid out his version of this idea in detail in a 1997 book called The Fabric of Reality, where he argued that quantum computers don't just hint at parallel universes, they actively rely on them to function. He's not a fringe figure either. Deutsch is a respected physicist at Oxford, often credited as one of the founding figures of the entire field of quantum computing theory, decades before any real quantum chip existed. Subscribe now, because this theory has been quietly dividing physicists for decades, and Willow just threw it back into the spotlight. Here's the basic idea behind the many worlds interpretation. In quantum mechanics, particles don't behave like normal objects. Before you measure them, they exist in something called a superposition, a strange overlapping state of multiple possibilities at once. Deutsch argued that every time a quantum event happens, reality doesn't just pick one outcome and discard the rest. Instead, the universe splits, and every possible outcome plays out in its own separate parallel universe. A coin that could land heads or tails doesn't really choose one or the other in this view. Instead, the universe branches into two complete copies of itself, one where it landed heads and one where it landed tails, with neither copy aware that the other exists. According to this interpretation, a quantum computer doesn't just process information in our universe, it spreads the calculation across countless parallel versions of itself, with each version handling a different piece of the problem, and then somehow the answers interfere with each other, canceling out the wrong paths and amplifying the right one. Nevin's argument is essentially this: if Willow finished a problem that would take 10 septillion years using only the computing power available in our single universe, then maybe it wasn't only using our single universe at all. This is your reminder to like this video, because the response from the scientific community to this claim was anything but quiet. Plenty of physicists pushed back almost immediately. Critics pointed out something important. The many worlds interpretation is just one of several competing explanations for how quantum mechanics works. There's also the Copenhagen interpretation, the oldest and most widely taught explanation, which describes quantum particles using probabilities without claiming that reality physically splits into multiple universes at all. Under this more conservative view, Willow's mind-bending speed is fully explainable using nothing but the strange, very real but single universe rules of quantum physics. In other words, you don't need parallel universes to explain why Willow is fast. You just need quantum mechanics, which is already strange enough on its own. This actually isn't even the first time Google has made headlines for a claim like this. Back in 2019, Google announced something it called quantum supremacy, claiming a previous chip had solved a problem in 200 seconds that would take a supercomputer 10,000 years. At the time, that announcement was also met with skepticism. Some researchers later argued that with smarter classical algorithms, the same problem could be solved on traditional supercomputers in a matter of days, not 10,000 years. That history matters here, because it shows a pattern. Big quantum announcements tend to get bold headlines first and careful, measured scrutiny second. Willow's 10 septillion year comparison may eventually face the same kind of scrutiny as classical computing techniques continue to improve. Subscribe if you're starting to see why this sparked a genuine debate among actual scientists, not just internet commenters. So, which side is right? Honestly, nobody knows for certain, and that's not a cop-out. That's the actual state of modern physics. The many worlds interpretation and the Copenhagen interpretation make the exact same testable predictions for how quantum experiments will turn out. There is currently no experiment that can prove one interpretation correct and the other wrong. Choosing between them right now is less about new data and more about which philosophical framework you find more convincing. That's exactly why so many physicists got frustrated with how Google framed the announcement. Several pointed out that calling Willow evidence for the multiverse blurs the line between a genuinely impressive engineering achievement and a far more speculative philosophical claim. Like this video right now, if you think tech companies should be more careful with headlines like this, because plenty of scientists agree with you, but let's be clear about something important. Even without the multiverse claim, what Willow actually achieved is still a massive deal. The chip demonstrated something called below threshold error correction, a milestone quantum researchers have been chasing since the 1990s. As you add more qubits to a quantum chip, errors normally pile up fast, because qubits are incredibly fragile and lose their quantum properties the moment they interact with the outside world even slightly. Willow did the opposite. Every time Google added more qubits, the error rate dropped instead of rising. Here's why that matters so much. Google tested Willow using grids of qubits in increasing sizes. A 3x3 grid, then a 5x5 grid, then a 7x7 grid. Each time they scaled up the grid, the error rate was cut roughly in half. That might sound like a small technical detail, but for decades, this was considered one of the biggest open questions in the entire field. If errors always got worse as systems scaled up, quantum computers would be permanently stuck as fragile laboratory curiosities, never powerful enough to solve problems that actually matter. Willow proved, for the first time, that scaling up doesn't have to mean scaling up the chaos. That single fact, by itself, is considered one of the most important quantum computing breakthroughs in years, no multiverse required. And Willow isn't operating in a vacuum. Just about a week after Google's announcement, Chinese scientists unveiled their own chip called Zhuchongji 3.0, also packed with 105 qubits, matching Willow almost exactly in scale. Researchers compared the two chips closely and found their performance was remarkably similar, with Google holding only a slight edge in precision, N. Since then, Chinese researchers have continued chasing the same error correction milestone Willow achieved, using a different microwave-based technique that some experts believe could eventually be easier to scale up. This isn't just a scientific curiosity anymore. It's becoming a genuine global race between two of the world's most powerful nations, each trying to be the first to build a quantum computer that can do something truly, unambiguously useful. Subscribe now, because understanding why this matters could change how you see the next decade of technology. Here's the bigger picture nobody puts in the headlines. A truly stable, large-scale quantum computer could eventually help design new medicines by simulating molecules in ways classical computers simply cannot handle. Drug companies already use early hybrid quantum methods to study how molecules bind together, since simulating these interactions with classical computers gets exponentially harder as molecules get bigger. Experts in the field estimate that meaningful commercial applications in drug discovery and materials science could arrive within 5 to 10 years once quantum hardware scales up with enough stable, error-corrected qubits. It could optimize massive logistics and energy systems, helping companies route delivery trucks, manage power grids, and price financial risk more efficiently than classical methods allow. And then there's the encryption problem, which is arguably the most urgent of them all. Much of the encryption protecting your bank account, your medical records, and your private messages today relies on math problems that are extremely hard for normal computers to solve, but that a sufficiently powerful quantum computer could potentially crack using something called Shor's algorithm. Experts estimate that quantum computers capable of actually breaking today's encryption standards are still roughly 10 to 20 years away. But governments and tech companies aren't waiting around. They're already racing to build and standardize new quantum-resistant encryption methods before that day arrives, precisely because the moment a truly powerful quantum computer exists, every old, unprotected secret encrypted with current methods could become readable. And yes, a mature quantum computer could massively accelerate certain types of artificial intelligence training and computation, combining two of the most disruptive technologies on the planet into one system. Willow is not that fully realized machine yet. It's a major milestone on a path that started over a decade ago, not the finish line. Google itself has been careful to describe Willow as a strong sign that large, useful quantum computers can eventually be built, rather than claiming the job is already done. Like and subscribe if you want to keep learning what's actually true versus what's just hype in the world of AI and quantum tech. So let's come back to the original question. Did Google's quantum chip really tap into the multiverse to perform an impossible calculation? The honest answer is that nobody can currently prove that it did, and nobody can currently prove that it didn't either. What we can say for certain is that one of Google's top quantum scientists looked at a real, peer-reviewed, published result and pointed toward parallel universes. Whether or not you believe that interpretation, the fact that a serious scientist felt confident enough to say it publicly tells you just how strange and unresolved our understanding of reality still is at the quantum level. We are not talking about random speculation from internet forums here. We are talking about an official statement backed by a peer-reviewed paper in the journal Nature from the team that built one of the most advanced computing devices on the planet. If this story changed how you think about reality, hit subscribe and turn on notifications, because quantum computing is about to get a whole lot stranger from here. Quantum computers like Willow are forcing physicists to confront questions that used to live only in philosophy classrooms. What does it actually mean for something to be real? Could there be other versions of you right now reading a slightly different version of this very sentence in a universe you'll never be able to visit or prove exists? If the many worlds interpretation turns out to be correct, then in some sense, every decision you've ever made that could have gone differently already did go differently, somewhere, in a universe permanently sealed off from this one. Science doesn't have a final answer yet. But for the first time, a piece of hardware sitting in a lab in California is forcing some of the smartest physicists alive to take that question seriously. And maybe that's the actual headline here. Not that Google proved the multiverse exists, because it didn't. But that a machine built from silicon and superconducting circuits got fast enough to make some of the world's leading scientists wonder, even for a moment, whether other versions of our universe might be doing the math right alongside us. Whatever interpretation eventually wins out, one thing is already certain. The line between cutting-edge engineering and genuine philosophical mystery has never been thinner than it is right now, sitting inside a refrigerator cooled colder than outer space in a lab in California. If this blew your mind even a little, like subscribe, and share this with someone who needs to hear how strange reality might actually be.